In our last video, we learned about the alternating series test. Now, in this video, we're going to learn about something called the alternating series remainder. And this is for a convergent alternating series. The partial sum S of n can be useful in approximating the total sum of the series. And so, first thing we got to do is alternating series remainder theorem. If a convergent alternating series satisfies the following condition, that our ace of n plus 1 is less than or equal to our ace of n, then the absolute value of the remainder, which we'll call r sub n, involved in approximating the sum s, the total sum, by our partial sum s of n, is less than or equal to the neglected term. That's the remainder. Okay, so let's write this in equation notation. So the absolute value of the sum minus the partial sum is equal to the absolute value of the remainder, which is less than or equal to our ace of n plus 1, our next term, once we stop with our partial sum term. Okay, so here is the proof of this. So we're going to let r sub n equal s minus s of n, our partial sum, which is equal to the summation of n equals 1 to infinity of negative 1 to the n plus 1 of a sub n, minus the summation of n equals 1 to n, that's partial sum, of negative 1 to the n plus 1 of a sub n. All right, so that negative 1 to the n, a sub n plus 1 plus negative 1 to the n plus 1 of a sub n plus 2 plus negative 1 to the n plus 1 times a sub n plus 3 plus ... If we expand that out, and then we can take that negative 1 to the n, factor it out, and we get a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3 plus ... So that tells us that our absolute value of r sub n, which is our remainder, absolute value of a remainder, is equal to our a sub n plus 1 plus minus our ace of to the n plus 2 plus our ace of n plus 3 minus our ace of n plus 4 plus ... And so our absolute value of r sub n is equal to that term that I just stated. And let's group some terms together. So we have our a sub n plus 1 minus our a sub n plus 2 minus our n plus 3 term minus our a sub n plus 4 minus our a sub n plus 5 term minus ... if we factor out a negative, which has to be less than or equal to our a sub n plus 1 term. Consequently, we can show that the absolute value of our sum minus our partial sum is equal to our remainder at our nth term, which is less than or equal to our a sub n plus 1 term. Okay, so let's see how this actually works when we do a problem. So approximate the sum of the following series. All right, so first thing we notice about this series, let's span it out so we see what's going on. So I have 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial ... Okay, so we have an alternating series. And then we know that since 1 over n plus 1 factorial is less than or equal to 1 over n factorial, and we also know that the limit as n goes to infinity of 1 over n factorial, well, that's equal to 0. Then we know that this series converges by the alternating series test. So I have to prove convergence first before I can use the alternating series remainder theorem, because it requires a convergent alternating series. All right, so let's do our partial sum to 6, because I got a few of those terms written down here. So let's do s of 6, because that was what it asked us to do, find the partial sum of the first 6 terms. So that would be 1 minus 1/2 plus 1/6 minus 1 over 24 plus 1 over 120 minus 1 over 720. And that's approximately 0.63194. And so by the alternating series remainder, you have the following formula. The absolute value of our sum minus our partial sum is equal to our remainder of the sixth term, which is less than or equal to ace of 7. Okay, so we need to figure out we need to know what ace of 7 is. So that's going back to our series and replacing every n with 7. And we get 1 over 5,040, which is approximately 0.0002. So R sub n equals our ace of 7, which is less than or equal to our 1 over that. So let's rewrite this. Okay. So absolute value means I can add or subtract each side to get the s by itself. So if I want to get s by itself, I could add or subtract that s of 6. So we have our s of 6, which is 0.63194, minus our ace of 7 term, which is less than or equal to our exact sum, which is less than or equal to our s of 6 plus our ace of 7 term. So for little calculator work here, I get that 0.63174 is less than or equal to our actual sum, which is less than or equal to 0.63214. So we can't find the actual sum of this infinite series, but we can narrow it down. We know the actual sum has to lie somewhere in between 0.6317 and 0.632. That's pretty darn narrowed down. Okay, that's the power of the remainder theorem. Okay, so again, we need to make sure we have a convergent series here. So since 1 over n plus 1 cubed is less than our 1 over n cubed, so this makes it a decreasing series, and the limit as n goes to infinity of 1 over n cubed is 0, we can say that this series is a convergent series by the alternating series test. Okay, we were given a little bit. We were given that our error is less than 0.001. So the error is the absolute value of s minus s of k, whatever our k value is. And that needs to be less than 0.001. 0.001, we can rewrite that as 1 over 10 cubed. And if I look, so that means my next term that would be smaller than that would be 1 over 11 cubed. So that's what we're going to go to. So that means I need to go to, my n plus 1 term is going to be 11. So that means I'm looking at the series. We're going to approximate our series for the first 10 terms. So that's going to be 1 over 1 cubed plus minus 1 over 2 cubed plus 1 over 3 cubed minus 1 over 4 cubed plus 1 over 5 cubed plus minus 1 over 6 cubed plus 1 over 7 cubed minus 1 over 8 cubed plus 1 over 9 cubed minus 1 over 10 cubed. And then typing all that into my calculator, I get a 0.901116.